We continue on by looking at example 3.1, a randomized complete block comparison of 5 treatments. A researcher performed an experiment to compare 5 treatments. The researcher needed 4 replications of each treatment. However, there was not enough homogeneous material available to be able to use a completely randomized design for the experiment. There was enough material to construct 4 blocks, with the experimental material within each block being homogeneous and containing enough material for 5 experimental units. The researcher therefore decided to use the randomized complete block design for the experiment. Within each block, each of the 5 treatments was randomly assigned to 1 experimental unit. Randomizations were performed separately within each block. At the end of the experiment, the response variable was measured for each experimental unit. So here are the data from the experiment, along with the appropriate summary statistics for performing an ANOVA in the context of a randomized complete block design. You can see here that we have the rows corresponding to blocks, columns corresponding to the 5 treatments. For each treatment, we have the sum of the treatments, the mean of the treatments, and the sum of squares, the uncorrected sum of squares for each of the individual treatments. For each of the rows, for each of the blocks, we have the block sum, the block mean. We have the overall sum of the observations, which is 819.9. And we also have the sum of the uncorrected sums of squares from each of the 5 treatments. And so this is the total uncorrected sum of squares. And so these values are used to calculate the appropriate sums of squares and then eventually the mean squares that go into the ANOVA table. So here is the preliminary ANOVA table showing the degrees of freedom. We have 4 blocks, so there are 3 degrees of freedom associated with blocks. We have 5 treatment levels, so there are 4 degrees of freedom for treatments. We have 20 observations total, so there are 19 total degrees of freedom. And then we get the degrees of freedom associated with the error term, either by subtracting the sum of the number of degrees of freedom for blocks and treatments from the total degrees of freedom, so 19 minus 7, which is 12, or we could also get these degrees of freedom by multiplying the degrees of freedom for blocks and treatments. So this is the degree of freedom information for the table, and it's always good to write this out, make sure that we understand the design and write this out correctly. It's called keying out the ANOVA table. To go any further, we've got to calculate the sum of squares, the total sum of squares, the sum of squares for blocks, and the sum of squares for treatments. Once we have those, then we can get the sum of squares for error by subtracting the sum of squares for blocks and the sum of squares for treatments from the total sum of squares. And then once we have those values, then we're off to the races, and we can calculate the corresponding mean squares and then the 2 F statistics. So we first calculate the correction term, capital C, and you can see the calculation here. I'm not going to spend much time talking about this. We've shown how to do these kind of calculations before, but again, the numerator here, the square of the total, the square of the sum of all the observations in the data set is obtained, if we go back a few slides, this is that sum right there. So this is the sum of all the observations in the data set. And we can get this either by summing the column sums or by adding up the row sums. All right, that's a good quality control check to incorporate to make sure that you've calculated the sums correctly. And so once we have that, then it's very easy, all right, to calculate the correction term. We just square that sum, divide by the total number of observations, which for a randomized complete block design is T times R, the product of the number of treatments and the number of blocks. And so anyway, we divide that by 20, and we get 33,611.8005. So that is the correction term that we subtract from the uncorrected sums of squares for the total, for blocks, and for treatments. Next, we calculate the total corrected sum of squares. And so we add up all of the squared values from the data set, right? And let me just go back here real quick to the summary table. That's this value right here. So 42,122.470. And from that, we subtract off this correction factor, and so we get 8,510.6695. Next, we calculate the block sum of squares, or the sum of squares due to blocks. And to get this, what we do is notice that the summation here, the index of summation is I, and in the context of this randomized complete block design situation, I corresponds to the blocks. So we're adding things up over blocks. What are we adding up? Well, we're adding up the square of the sums of the blocks, or adding up the square of the block totals. Once we get that, we divide that by the number of treatments. All right. So we want to make sure that even though we're adding up our things here, the mathematics tells us we need to divide that by t, and then once we have that, we subtract the correction factor. So let me just go back to this summary table, and we are squaring these sums here, adding those squared values up, and then dividing by 5. Okay? And then once we have that, we subtract off again the correction factor c, and so we get 7,088.6335. And then finally, the sum of squares due to treatments, we add up the squared treatment totals. Once we have that sum, then we divide that by r, the number of blocks. And so again, going back to the summary table here, we are squaring these quantities, adding those squared quantities up, and there are 5 squared quantities that we have to add up, and then we divide that by 4. And then once we have that, then we subtract off the correction factor, and so we get 1,224.3070. All right, so now we have enough to start populating the ANOVA table. So I've entered the sum of squares for blocks, the sum of squares due to treatments, and the total sum of squares. And so now we can get the sum of squares error by subtracting from 8510.6695 the sum of the sum of squares for blocks and the sum of squares for treatments. And so doing that, we get 197.7290. And now, once we have all of these sums of squares, we can compute the mean squares by dividing each of these 3 sums of squares by the corresponding degrees of freedom. All right, and so the mean squares for blocks is 2362.8778. The mean squares treatments is 306.0768. And the mean square error then, which remember is our estimate of sigma squared, which is the variance associated with the model error term, that estimate is 16.4774. Once we have these mean squares, then we obtain the corresponding F statistics, the F statistic corresponding to blocks and the F statistic corresponding to treatments, by dividing their mean squares by the mean squared error. Now, we're really not too much interested in this, at least at this point, this F statistic for blocks, all right? But we are very much interested, this is the primary focus, the F statistic for treatments. And this is what we're using to test the hypothesis, in particular the null hypothesis that there is no difference between the 5 treatment means. We can try to interpret this F statistic for blocks as some measure of the effectiveness of blocking. But again, it's just, the larger that F ratio, the more evidence there is for an effectiveness of blocking. But we really can't attach a true significance level or p-value to that because we don't have replication of individual blocks. Okay, so let's look at the hypotheses that are tested by the ANOVA. The treatment effects in this particular situation were the only treatment effects that were of interest to the researcher. And because of that, the treatment effects are fixed effects. So this is a fixed treatment effects model. And so the parameters associated with the treatment means would be mu1 up through mu5. All right, and the null hypothesis then that is being tested by this ANOVA, right? So this particular, and in particular, this particular F test, or this F statistic, 18.5755, the null hypothesis is that there is no difference among the 5 treatment means. The alternative would be that differences do exist among the treatment means, that at least one of the means is different than the rest. And let's go ahead and use, so let's say, a 0.05 level of significance. And then if we use a 0.05 level, then the degree, the critical point comes from the F distribution with 4 numerator degrees of freedom and 12 denominator degrees of freedom. And in particular, it's the upper 0.05 percentage point, the upper 5th percentage point for that particular F distribution. And so we can look that up in the F table, and that F, or that critical point, is 3.26. And so because our F statistic, which we denote by F sub t, I need to fix that right there so that it corresponds to our notation that we're using. Okay, so that's better. All right, so since our test statistic for treatments, F sub t, which, recall, was 18.5755, because that is bigger than 3.26, we reject the null hypothesis and conclude that differences exist among the mean responses of the 5 treatments. And so because of that, follow-up comparisons of some form would be warranted. And if there were some kind of structure to those treatments, then perhaps that structure would suggest the kind of follow-up comparisons that would be appropriate. For example, maybe treatment 1 is a control, and the primary interest is in comparing each of the other 4 treatments to the control, and there could be other scenarios as well. Now, note that in this particular situation that the critical point, the F statistic is very significant. It's quite a bit larger than the critical point. And that translates into a very small value for the p-value. And in fact, the p-value is less than 0.0001. And in fact, we'll find the exact value here in a second. Now, one way that we'll do that is I'm going to show you how to do this with a calculator in case we're doing calculations by hand and we don't have output from SAS or R or something like that that we can rely on. And so what I've done here is used the FCDF functionality in the TI-84. And so this shows here the face of the TI-84 calculator, and notice that I've got the red button here is this button here, the VARS button, is highlighted red. What's happened here is that I pressed the second button and then I pressed the VARS button. And so we're invoking or pulling up the distribution menu. And so this first, the screen here in the upper left quadrant, it shows the distribution menu. And the option that we want is down here below option number 9. And so I've scrolled down, and we can see here that the option that I want is it's labeled 0, okay, for 10. And anyway, so this is the FCDF function that's built into the TI-84 calculator. And so when I select that by pressing the Enter key, then it brings me to this wizard where I can enter in the lower point, the upper point, delineating the interval over which I want to calculate this probability. And I also need to specify the numerator degrees of freedom and the denominator degrees of freedom. Now remember that we have 4 numerator degrees of freedom and 12 denominator degrees of freedom, so that's what I enter. Once I fill those values in and press the enter key, then it pastes that into the calculator screen, calculation screen. And so then we see here that the resulting value, which is the p-value for this test, turns out to be 4.456 times 10 to the negative fifth. All right, so it is a very small p-value, and so this there's strong evidence that the null hypothesis here is not true. There is strong evidence that at least one of the treatment means is different than the others. Okay, here is another way that we could calculate this. I've constructed a spreadsheet that is consistent with the calculations that we've got in the notes. And you can take a look here. You can pause the video. You can take a look and make sure that well, we've entered the data correctly. And note that I've constructed this to look, really as much like the lecture slide that had the summary table as possible. So columns correspond to the treatments, rows correspond to blocks. I've got the summary statistics for each of the columns. I also have summary statistics for the rows, and I have a few extra summary statistics in here, but I certainly have the ones that I need. And then using those calculations, I calculate the correction factor C, the total sum of squares, the sum of squares associated with blocks, the sum of squares due to treatments, and then from that I can get the sum of squared error by subtraction. Now I really wouldn't need to have SSE, the sum of squares error, right here because I calculate that down in the ANOVA table by subtraction as well. So anyway, you can pause the video and go back and compare this to the values that we obtained when we did the calculations by hand. But I think you'll see that we get exactly the same number in each of those cells. And also, we're using the FDist, in this particular spreadsheet that I'm using, which is the OpenOffice spreadsheet. The function for the F distribution is called FDIST, FDist. And you enter that into the cell, and then the first argument is the value of the F statistic, which would be 18.5755. The second argument is the number of numerator degrees of freedom, which is 4. And the last argument, the third argument, would be the number of denominator degrees of freedom, which would be 12. And so then it calculates the p-value automatically. And so we can see that p-value is 0.00004456, which is consistent with the value that was given by the calculator. Now another way to do this would be to perform the analysis using SAS. And so here is a little snippet of my SAS program that I used to do this as well. So a SAS analysis using proc mixed. Now when we're fitting a randomized complete block model, we cannot do that with proc GLM. Proc GLM does not have the ability to correctly analyze data or a model that has random effects. It has a random statement, but it's not used for what you would think it would be used for. So don't be confused by that. I think a lot of people have been tripped up by that in the past. But that's in order to do this, in order to fit a randomized complete block model, we have to use a procedure that can fit random effects, and there are at least 2 procedures in SAS that will do that. One is proc mixed, as we're seeing here, and the other would be proc glimmix. Now, one thing that I'm doing when I invoke proc mixed, I'm telling it to use the method to use, and there has several methods. One is maximum likelihood. Another method is residual maximum likelihood, sometimes called restricted maximum likelihood, but the appropriate term is residual maximum likelihood. there is also a type 3 method, and the type 3 method is the kind of analysis that we've done by hand, all right, by calculating sums of squares and so forth. And so I've chosen to use this so that you can see how we get consistent results with the way we've done it by hand using SAS. Now let me just talk a little bit about this. You're familiar with ProcGLM, and so in ProcGLM, in order to fit a linear model, we have to identify the classification variable in our model. And so, for example, in this data set, the classification variable that identifies the treatments is called TRT for treatment, obviously. In a randomized complete block model, we also have to have a classification variable that identifies different blocks. And so in this particular data set, I've called that variable BLK for block. And then the way that we specify the randomized complete block model in SAS, at least one way to do it, there are a couple ways to do it, but one way to do it is to specify the fixed effects part of the model first, and that is done with a model statement. So model, and then the response variable, which in this data set is y, equal to, and then the classification variable that identifies the different treatment groups in the data set. And then we have to specify the random part of the model. Excluding the random error term, we never have to enter that into SAS explicitly. All right, but the blocks are considered random, and so we have to enter those into the model. And we have to specifically tell SAS, ProcMixed, that blocks are random. And so, in fact, if we were to put BLK block up in the model statement, it would do an analysis, but it would not treat blocks as random. It would treat blocks as fixed effects, and that's not what we want typically when we are conducting a randomized complete block experiment. So we have to tell SAS ProcMixed that block is random, and we do that very easily with and intuitively with the random statement. So we say, we issue the random statement, which says that the variable or variables that follow are random effects. And we have one random effect besides the random error term in this model, that is block BLK. And so we just specify that. And so for a randomized complete block model, that's all we have to do in order to set up the model correctly. And so let's take a look at the output. And so we can see here that this is a snippet from the SAS output. And we have here the ANOVA table. And SAS ProcMixed is producing this ANOVA table explicitly because I specified method equal type 3. If I did not specify method equal type 3, if I didn't specify any method at all, then it would default to residual maximum likelihood. That's its default. If I issued something like method equal ML for maximum likelihood, or method equal REML for residual maximum likelihood, which again is the default, then it would give me results for the significance of treatment, which is really what I want, but it would not put that into the structure of a ANOVA table like we have here. But I wanted to produce this kind of output so that we can compare the results that we got, in particular the sums of squares for both treatments and blocks, and residual or error, the mean squares, and then the F statistics. Now, one thing I would also point out that SAS ProcMixed, when we specify the method equal type 3 option, then it's also going to give us a column of expected mean squares. And so what we see here, and SAS has a computational way of determining what the expected mean square values are. And so we see that the expected mean square for error is the variance of the error term, sigma squared, so and that's what we know. The expected mean square for the treatment effect, for the treatment mean square is sigma squared plus a quadratic. This is a shorthand representation or notation for a quadratic form involving treatment. And so that would tell us that it's adding, there's a plus a positive value here. This is going to be 0 if and only if all treatment means are equal. And then the expected mean squares for blocks would be sigma squared plus 5 times the variability of block. And if you go back and compare that to what we had put down in the notes, you'll see that that's consistent with what we included. So that's how we can do an analysis for a randomized complete block design. As you see, the calculations are fairly straightforward. They're easy enough that we can actually do them by hand. It's not too bad to do that, not too hard to do that. We can create a little spreadsheet to do it. And we can also invoke something a little heavier duty, a little bit more heavier firepower, like SAS to do it. You can also use R or Minitab, Stata, SPSS, a variety of packages. All right, so now I want to ask you a question here. I want us to think about something. What would happen if we ignored blocking in the analysis and instead analyzed this data as having come from a completely randomized design? So, perhaps, maybe maybe we are statisticians working with a researcher, and perhaps we did not do a very good job of inquiring with the researcher how they conducted the experiment. Maybe we just assume, for some reason, that they used a completely randomized design. So what are the implications of ignoring blocking in the analysis and using an ANOVA for a completely randomized design? Well, if we do that, then let's take a look. Let's go ahead and do that kind of analysis. But let me just start off. Let me preface this by saying you would never want to do this, all right? If data have come from a randomized complete block design, you don't want to analyze it as if it's come from a completely randomized design. And so, what I'm trying to show here are the negative implications of doing that. So I'll let you go through and do the calculations. I've got the calculations here on the slide in the video, and you can compare the results and make sure you get the same values. Okay, and so here would be the keyed out ANOVA table. We see that we now do not have a row for blocks because we're ignoring it in the model, right? We've got the sums of squares for treatments and the sum of squares total. We get the sum of squares error by subtraction. And then once we have those values, then we're off to the races, as they say. And we calculate the mean squares and the F statistic. Wow, look at that F statistic. Remember that when we do an ANOVA, we're looking for F values that are greater than 1. Values of F greater than 1 that's what indicates that the null hypothesis is perhaps not true. If we see a value of F close to 1, then that would indicate that there's not much evidence that the null hypothesis is false. And when we have an F value that's less than 1, well, there's really a lack of evidence. And so we have a very small F value here. And so we see that based on that analysis, and again, let's go ahead and use a 0.05 level of significance. And by the way, in this situation, the reference distribution is the F distribution with 4 numerator degrees of freedom, but 15 denominator degrees of freedom. And so because the denominator degrees of freedom are larger, the critical point is smaller. Instead of 3.26, in this case it's 3.06. But still, even with that slight reduction in the critical point, the F statistic is so small, 0.63, it's not larger than that critical point. And so we would fail to reject the null hypothesis. And in fact, the p-value for this test is quite large, 0.6485. And again, we can find this p-value using the TI-84 calculator. And according to the 84 calculator, the p-value is 0.6486. Now, the slight discrepancy is because I've plugged in a value of 0.63 for the F statistic. The actual value of the F statistic, if we were to show more decimal places, it's 0.63 something. So it's a little bit bigger than that, if I remember correctly. All right. But so we see that the p-value is 0.649 if we round that to 3 decimal places. Okay, and again, here's a spreadsheet showing this calculation, and this is the same type of spreadsheet that I used back in the previous module for completely randomized designs. So again, we're ignoring blocking in this ANOVA, right? And so anyway, we see that the p-value is 0.6485. And so let's take a look at, let's think about this. So the negative impact of performing a completely randomized design ANOVA, which again is the incorrect analysis on RCB data. So analyzing the data as if it came from a completely randomized design is an invalid analysis. All right, it's invalid because the data did not come from a completely randomized design. The data came from a randomized complete block design. All right, so in order for an analysis to be valid, the analysis has to correspond. It's got to be the appropriate for the design of the actual experiment. So number one, the p-value is not correct. All right, that's what we mean when we say that the test is invalid. We're not going to be able to get a legitimate p-value from an invalid analysis. Now, by ignoring, here's the other thing. By ignoring blocking in the analysis and instead using an analysis for a completely randomized design, the model fails to account for the variation in the experimental material from one block to another. It fails to account for it because there's no term in the model that could potentially account for it. The only place that variation can go is in the error term. Because the block-to-block variability is unaccounted for, it ends up in that error variation, right? All unaccounted for variation ends up in the error variation. And that results in an inflated error variance estimate. And that has the result of drastically reducing power for the ANOVA, and also in decreasing the precision of estimators. We didn't construct any kind of confidence intervals yet or calculate margins of error, but if we had, we'd see that the confidence intervals based on this particular incorrect model would be much larger, much wider than the correct intervals would be had we calculated them from using a correct model. So the bottom line of this is that you must always use an analysis that corresponds to the design of the experiment. And that's why a course like this is so important. Because we have, number one, not only from a planning standpoint, so, prospective, looking into the future, well, let's design an experiment in this particular way for these reasons. But a lot of times, if you're a statistician, if you're a consultant, you'll have people coming to you after the fact, after they have performed the experiment, and ask for help with analysis of the data. And in order to perform an appropriate analysis, you have to understand very specifically the design of the experiment that was actually conducted. Not only the one that was planned, but the one that was actually conducted. So this is a good place to stop this particular lecture video. I've got another short segment that I want to include, but I'll put that into a different video. And so I'll see you in the next one.